and welcome to the last lecture in this series. So this will be all about orientation. So last time I sketched an argument that having a non-vanishing, nowhere vanishing n form on a smooth manifold gives rise to a system, a collection of charts, an atlas in fact, such that with the property that the transition functions have positive determinants of their derivatives. And such an atlas is called an oriented atlas. And the way we picked out this atlas is quite simple. We just pull back the form to an open set in Rn. And once we pull it back, it will be some function times the standard n form, and we demand that the function be positive. Well, the moment you pick out those charts which have this property, then we showed that the transition functions have the required property, namely this thing here. This is the object we are concerned with. So right, and this turned out to be positive because this is positive as well as well, the right side, this is positive. Now two things, so what we have to check is that so what we have shown is that we can define a system of charts this way, but it's not clear that, well, to begin with, are there any charts of this form, and are there enough of them to cover M? Well, both questions are easily answered by noting that we can always get such charts. So note that if U alpha phi alpha is any atlas for M, not necessarily oriented, we can modify the chart diffeomorphisms. Let's call it phi alpha tilde, so that U alpha phi alpha tilde is this is an oriented atlas. So, and since the original collection of open sets U alpha covered M, and this will, well, we are not really changing the U alpha at all. So this the fact that these cover M is follows from the original property. Then the only thing we are changing are these maps phi alpha, and the way we modify them is, so recall that what we need actually to conclude, to get an oriented atlas, is that this when I pull back the form to Rn, I should get a positive function here. This f should be positive. So let's start with a chart and pull back U alpha phi alpha is a chart, and phi alpha inverse star omega equal to f dx1 dxn with, here I make the observation that by always taking slightly smaller charts if necessary, smaller open sets U alpha, we can assume U alpha is connected for all alpha, and hence so is phi alpha u alpha. These open sets in Rn that we get, we can assume are connected. Well, once it's connected and I write it like this, then I know that this is a nowhere zero form. This side, the left hand side, is nowhere zero. Therefore, this function is nowhere zero. Hence, it's either strictly positive or strictly negative. So if it's strictly positive, we are in good shape. So if it's strictly negative, then define what I'll do is I'll just interchange, use a reflection in the first two coordinates in Rn. Then define T from Rn to Rn by T of x1, x2, etc., xn to be just x2, x1, x3. The other stuff, other coordinates will be kept as they are. So I just interchange. This is a linear map, and therefore its derivative dt is just itself dt of well, c1, c2, cn is c2, c1, cn. And the main property of this that we need is if you write down the matrix, it's just similar to what we had done earlier. The determinant of the derivative of this is actually equal to -1. But what we need is that it's negative. So then let phi tilde, the new chart map, be phi tilde of phi tilde alpha be, first let's do phi alpha and then compose with this t. Well, so now let's see what the pullback form looks like. When I pull back this, I'll get this. Oh, actually, when I do inverse, already the order gets switched. Phi alpha inverse would be phi alpha. First, I'll have to do T inverse, then phi alpha inverse. And then I have to do a star, in which case the order again gets flipped. T inverse. Also, yeah, the way T has been defined, actually T inverse is equal to T. If I apply T twice, I'll just get back the original one. So I need not actually continue to write T inverse, but let's just T compose with T upper star, compose with phi alpha inverse upper star omega is equal to, this was what we had called f, T star of f of well, dx1, so which is omega naught. I'm using the notation omega naught for the standard n form. So this is equal to this, and this we know is the same thing as f compose with T and here is the, actually at this point is we know that for a linear transformation, this will be determinant of t, and then actually here I did determinant of derivative of t, but in this case I really don't. Yeah, okay, maybe I can use that. It will be the same in this case, determinant of dt times omega naught, which is minus f composed with t of omega naught. So in short, for this new chart map, I got a function here which is strictly positive because f itself was negative. So just by modifying this, by interchanging the first two coordinates, I can rectify so that I have this required property that all of these functions here are positive. And moment I do that, we have seen that we'll get an oriented atlas. And conversely, if you if this is an oriented atlas, phi alpha, u alpha, phi alpha is an oriented atlas. Suppose that u alpha, phi alpha is an oriented atlas. We would like to construct come up with a nowhere zero n form on the manifold. Well, we can certainly do that. So on locally, in fact, we don't even need oriented atlas. Let like in the previous construction, we had an n form on the manifold and we used charts to get an n forms on open subsets of Rn. Here we go the other way. So take a chart. Here you have the standard n form omega naught, and this is the chart map phi alpha, u alpha. So I just pull it back to u alpha, phi alpha upper star omega naught, and this will be defined on u alpha. Well, now the question arises as to how to patch these up. So these are on every open set we have got an n form, and we cannot ensure that, for instance, that suppose I have a phi beta, and on this intersection this form phi alpha star omega naught and phi beta star omega naught, that they actually agree on the intersection is something that we cannot ensure. So here we have to use a device which I didn't actually have occasion to use throughout the course, but which is actually one of the most useful things in the context of starting with locally defined objects and getting a global object on a manifold. Namely, this thing called here we use a partition, what is called a partition of unity subordinate to U alpha, the open cover U alpha. So now let me briefly say what this is. I won't go into the construction of this. So this is a collection of C infinity functions on M, which I denote by rho alpha, the same index set as the as the cover, such that the support of rho alpha is contained in U alpha. Each rho alpha, values of rho alpha lie between 0 and 1 for all x in M. And here's the last one is the reason why this name partition of unity is the reason why this phrase is used, partition of unity. So the summation of rho alpha x over all alpha equal to 1. Now for this to even the last condition for this condition to make sense, one needs this. First of all, we cannot ensure that the set of indices alpha is countable, let alone being finite. I mean, if it's countable, at least one can interpret this as a series, but alpha need not be a countable index. Alpha is basically keeping track of how many the charts covering the manifold. Well, but what one can ensure is so note that we can find a collection, a covering of M by charts which is locally finite, i.e. if P is in M, we can find a neighborhood of P, which let's call it UP, such that UP intersection this U alpha is empty except for finitely many alpha. So in other words, if this is P as a UP which will intersect only finitely many. Right. So in particular, every P is contained in only finitely many U alpha. So once one has this, the moment you take so here to interpret the last condition 3, if you take a specific x, we know note that we can find a covering of by charts which is locally finite. So here, of course, actually we already started with a system of is an oriented atlas. So what I need is that note that we can find a covering of M by, we can find a subcollection of U alpha, the same U alpha, which is a covering, still a covering, subcollection meaning we can discard some of the original U alphas, and which is locally finite. When I say note that this still requires a proof, it's just that it's a topological argument and I have no time to go over it. So let's just assuming it. So instead of saying note that, let me just say fact. Perhaps that's a better way of fact. We can find a subcollection of the U alpha which is a covering and which is locally finite. We can find a neighborhood such that finitely many U alpha. Right, once we have this, then every P is contained, so this becomes a finite sum, the sum in part 3, because the P is contained in only finitely many U alphas and the support of rho alpha is in U alpha. So the moment this X is not in a U alpha, rho alpha will be 0. So except for finitely many alphas, all the rho alpha X will be 0. So therefore this makes sense. And in fact, this says that not just at a specific X, in a neighborhood UP, also the same functions will survive and all the others will be 0. So once we have this, then we can define our global form. Define omega equal to rho alpha and then phi alpha star omega naught. And now the point is that here, so this is if rho alpha phi alpha star omega naught, of course this phi alpha star omega naught is defined only on U alpha, but the support of rho alpha is a closed set inside this. This is support of rho alpha, and this is equal to, so what we do is we define it to be identically 0 outside U alpha. So elsewhere it is 0. On U alpha, this is given by rho alpha. This is what this notation means. It's understood that this thing is identically 0 outside. So each term makes sense, and then we as a global form on M, and then we add it all up. The thing is that this is now all one has to do is check that this is nowhere vanishing. So if I take a specific P, so or rather X, omega at X is rho alpha X, and then this. Now because of this partition of unity condition, only finitely many alphas will survive for which this rho alpha X is not 0. Suppose rho alpha X is equal to 0 if alpha is not equal to one of these finitely many indices, then omega x will be rho alpha 1 x phi alpha 1 star omega naught, etc. Phi alpha k star omega naught. Well, we still haven't used the condition that we started with an oriented atlas. I could have done all this starting with any atlas. Now the last step is to say that this is not 0. At any x. And here's where we use the oriented atlas condition. So basically what I'll claim, essentially I just want to relate phi alpha 1 star omega naught. Of course, this entire thing evaluated at x. Everything at x, etc. So phi alpha 1 star omega naught, we know that any two n forms are multiples of each other at a specific point. So if I fix x, then this is some constant times, let's call it c1 times. Actually, let's use phi alpha 1 star omega naught as the base. So let me start with 2 onwards. So I want to compare everything else in terms of phi alpha 1 star, and then alpha 2 is, let's call it c2 phi alpha 1 star omega naught. And here's the main point, the fact that it's oriented charts will imply that this C2 is positive, because after all, what is C2 is positive, because C2, to figure out what C2 is, just rewrite it like this. The usual thing of using a transition function. So essentially, I throw in the inverse of this, and then this, and then phi alpha 2 star. Then I take the inverse inside and so on, and star outside, and then finally I'll get phi alpha 1 inverse composed with phi alpha 2 whole thing star, and then phi alpha 1 star omega naught. That is assuming that alpha 1, this u alpha 1 and u alpha 2 intersect. I mean, if x is, if rho alpha x is not 0, then they have to intersect. So I get it like this, and therefore, and as we have seen many times, when I pull back by and here the star means the derivative and so on. Here it's not quite the transition function, but it's the sort of reverse of the transition function. But at any rate, what will play a role is the derivative, the determinant of the derivative of this will come into play. Then using the fact that transition functions are positive, then one can prove that this determinant is also positive. Ultimately, so one ends up getting this. So you'll have an expression like this. Yeah. So the first term I keep it as it is, phi alpha 1 star omega naught plus C2 times rho alpha 2 x phi alpha, again the same term, and so on. So finally, I'll end up with this plus C2 rho alpha 2x dot 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 plus ck rho alpha kx whole thing multiplied by, well, rho alpha 1 star omega naught. Now the point is that since this is summation of the rho alphas is 1, at least one of these rho alpha 1, rho alpha 2 should be positive, and the C's are already positive, and all the rho alphas are non-negative, so therefore the entire sum should be strictly positive. So therefore this is not 0. It's just a positive multiple of this. So this completes the brief sketch, and we'll stop the course at this point. As I said, one would then next talk about integration on manifolds, and after introducing manifolds with boundary, and then finally move on to Stokes' theorem. And when the whole theory of differential forms is crucial for even to talk about integration on manifolds. Yeah, okay, so thank you. So we'll end the course at this point. A natural starting point for subsequent study will be a little bit more about orientation, examples, and so on. And then one can read some material about manifolds with boundary, then integration on manifolds. Then finally, one will have Stokes' theorem on manifolds, which is a very useful tool and generalizes all the classical Stokes' theorem in R3, Green's theorem in R2, and so on. So thank you.